going to introduce you to Paul. Paul has over 30 years experience in the electrical service engineering discipline. He is mainly focusing on specifically low voltage switchgear. He is currently the Quality and Technical Solutions Manager with ABB, and he's the current chair of the NSAI ETC TCO4 committee. He's also an IEC member, and he is a SAC CE approved service engineer. Paul is the holder of a BSc honours degree from the TU Dublin School of Electrical and Electronic Engineering. He's also in the final stages of a master's program in that school. He's in the final stages of that master's program. Yeah, and at that point there, I will hand it over to you, Paul.
Thanks, thanks a lot, Anthony. Sounds really good, doesn't it?
Yeah.
But anyway, listen. Hi everybody, and look, thanks for taking the time to join me on this CPD, and thanks for Engineers Ireland for allowing me to speak. I'll get straight into it. So today's topic is on low voltage selectivity. Just see if we got. Okay, Neve, keep an eye on the screens for me, but. Just to get a start, so the low voltage selectivity CPD, it's actually part of a series that I put together through COVID. It was an online campaign that I done to try and keep engineers engaged while we were all sitting at home. And so I do one on the low voltage switchgear and panel selection, and then I do another one on the 61439. So maybe another day we can all look at that. I do a CPD on low voltage solutions, the new way of thinking, and then the oddball out is the AFDD for it's the arc fault detection. So moving on,
Paul,
I won't.
Paul, just
yes?
your presentation isn't up on the screen there at the moment.
Oh, isn't it?
Seems to just
Okay.
disappeared. If you just want to share screen again.
Yeah. Try that now. Are we back on?
You're back on. Perfect.
All right. Yeah. Thank you.
Thanks.
That was whether it was a good or a bad start. There was nothing there to say anyway. Everything that's on that list is what Anthony already called out. But just to show you, just for today, when I started this campaign, I bought a little dog, that's Colin and Gardy, and the only reason I'm bringing them into this is because I am at home, and I'm on my own, they're out the back. But if they do make a bit of noise, I apologise, right? So they get a bit needy at this hour. So just to get straight into it, because we keep an eye on the time. So circuit breaker selection. Why is it important? How to calculate a fault. We won't spend too much time on that, but let's talk about it anyway. Some discrimination or selectivity types. Backup protection we'll do at the very end. Current limiting breakers. Definitions I'm going to leave out for today. They're on. When you get a copy of the presentations, they're at the back pages. You can look at them yourselves. So, I know there's a lot of engineers on here, and a lot of this low voltage selectivity presentations is old rope, we'll say, for some people. It'll be new rope for new engineers, but it can be old rope for some. So why is selectivity and coordination important? Let's get the brain into some, kick it into gear first. So we've safety on site. We have identifying the problem, the zones. This one here, the limiting the stress of the components, I suppose that's something that I emphasized. I stopped there is because at the end or all the way through, we will still talk about the stress, because people think selectivity and breakers, they take all the problems. Stress goes, like all of us, goes through everything. Guaranteeing the continuity, but realistically, what we're trying to do is we're trying to compromise. We're trying to compromise between reliability, sustainability. Anybody who's done this with me before would know sustainability used to say simplicity. Sustainability is a much better word. And economy. So that's the goal. In order to get somewhere to start, we have to start at the beginning. So a single line diagram, we're all familiar, or we've all seen them, whether we've used them, drawn them, or just worked from them. We're very familiar. But what I'm going to point out here at this stage is the rules as such is we have 100 amp load, we can have a device equal to or slightly bigger than 100 amps. But in this case, we have a 100 amp device. T2. That could be an X2. This is an old drawing, so it'll be an XT2. But you can see from the one above, and the reason I'm pointing out the circle, it's a T5 400 amps breaker. Now, realistically, that's probably not making an awful lot of sense, because you might have a QF6, QF7, QF8. Then that one 400 amp breaker would make a bit more sense. But if you only have two, if you only have 100 amps and you only have one breaker upstream and you want selectivity, you can see where you have to jump in sizes, or jump in current, or jump in family. Okay, so that's just keep that in mind as we go through. Okay, so calculating a fault. When we're calculating a fault, I don't know about all you, I never remember this. Learned it so many times. So I have a wrote on the table. It's actually wrote on the table beside me. But look, we won't worry about how to do it. We just know that we can mathematically calculate a fault by using the kVA of the transformer. But more often we'll just use a chart. This one is taken just from a catalogue. Used to have this on a mouse, which was great, but somebody stole it on me. But as we can see, with the 16 kVA transformer, the chart tells us that it's 35.7 fault rating Ka, whereas the mathematical one we got 38. So but realistically, it doesn't make much difference to us, because we still have to pick a device in around that size. So then you've got the software. The calculating a fault is done so much easier now, because we just turn on whether we Trimble, ERAX, ePower, ABB, Partner Hub. I've given those links. They're all free softwares that you can use from ABB to give a single line diagram, and that will also give us a fault rating. And for this stage, we're going to work at 35 Ka of 38 Ka. So we know the fault rating, and we have to pick a device. And this all makes sense as we go on. This is just getting us warmed up, as we say. I will keep an eye on the time, so I won't get us warmed up too much. But when we're looking at a breaker for something like to cover 38 Ka fault rate, we're actually, whether we mention it or don't mention it, we're looking at the ICU value. So it's the ultimate breaking capacity of the breaker. And you could say, just for this one, we cover it with an E1.2. Whether it's 630 amps or 1600 amps, it's not too important to us. It's the fault rating that we want to know about. And the fault rating at this one would be 42. And that's why sometimes mathematically we can do these calculations very quick and get a good idea as to where we're going to go from. But that's the ICU. We will talk. On one of my other CPDs, we talk in detail on what all those ICU, ICW, all those things mean. But for sure, we'll brush on them as we move on. So now we're all warmed and ready, and the tea is on, and everybody's happy. So what we're going to look at on the agenda is we're going to look at some current selectivity and time, or as probably we all would know, it's time current is the way it's referred to in most softwares that we use. Energy selectivity, which is probably the confusing side of selectivity when we get the curves. Time current is quite easy. Zone selectivity is a bit more advanced, and selectivity using Goose. It's yeah, we'll as we get there. If you're familiar with it, great. If you're not, it'll be, excuse me, a nice new topic for you. Now, without kind of insulting anybody, I don't want to insult anybody, but selectivity, what we understand since we were apprentices or junior engineers, since we went our first technical school, is it's pretty much common sense. Selectivity, what does it mean? So what does it mean? So when an overload occurs or a short circuit in a particular area, when there is selectivity, now we also state, I suppose I have to say that doesn't matter how many hierarchies of breakers is in line, all the breakers see it because it comes from the transformer or the source down. You can see I talk with my hands, that's why I leave my camera on. They come down through, so that although the fault might be at the very bottom, closest to the last breaker on the line, all the breakers in the line see it. So that's just where it comes in from we just say it comes in the back door and all the way down. So when we have selectivity, the downstream device opens. So the one closest to the fault, that's the one that trips, and everything else stays in play. And that's what we want. That's perfect situation. Whereas When we don't have selectivity, exactly the same situation. If there's no selectivity, upstream voice can go. It can go, two of them might go together. We just there's no selectivity, so we don't know. When that happens, if you go back to the page 1 where we had the single line diagram and we were looking at, the T5 400 feeding the T2 100 seemed like a big cost. Now it makes sense. It's not a big cost when we see the end result. So we've lost all the services, and that's not good, obviously. So we can see though a lack of coordination. Now I throw in all of the different terms because coordination, selectivity, discrimination, they're all pretty much the same thing. They're just used by different manufacturers and different people. It depends on where you. I use selectivity. It's my word. But lack of coordination, where a small problem becomes a big problem. Now we go back, say 20, 25 years ago when we had, when we lost one supply and took out the office and we all could go home early because the heating wasn't working, we were all very happy. We didn't know really. It wasn't as big a fuss. But now with data centers and hospitals, and we can't switch anything off. So therefore, selectivity is extremely important. Now, it's a good thing to know at this point that selectivity is for sure, it's an engineer's design. It's a design that you design to say whether it should be partial or total. And sometimes we'll be talking about that now. Sometimes that's can be an agreement, or it would depend on. We all want total. That's what everybody will ask you for. Oh, I want total selectivity. But then you have to explain partial selectivity might give you exactly what you want. But if you put in total, you're going to get a fail. And I'll explain that in a couple of minutes. But also, because it's an edge, it's now don't get me wrong, it's not a mandatory thing. It's an engineer's design. Now, as part of a contract and as part of that legally binding agreement, then it's mandatory. But on its own, it's an engineer's design. So it's your responsibility. And you decide what's best on the conditions that you have with your customer. That's just something to. We'll go back there for a second. No, I'll skip that one because I mentioned that at the start. It's just called them. So traditionally we have current and time and energy. They're traditional. And then we have the zone selectivity and Goose, which are there kind of advanced, which you said that at the start. So I'll just move on. One important thing, and it's one thing that I do when I help a lot of people with studies. As ABB, we don't actually do studies per se, because we'd have to take, like most manufacturers, take an awful lot of responsibility for the world if we did. So we help an awful lot of people with studies. And I do a lot of helping with people. But one thing I try to do at the beginning of a selectivity study is that I use the online tool to show the breakers I select, will they actually work together? That's an important thing. So we go through, old time used to be coordination tables, PDF. They've been gone since about 2011. And now everything's online. So because it's up to date, things change rapidly. But the reason I brought this one up is because I know, because I'm ABB, I know that an XT4 is an ABB device and an XT2. I know that they are good selective products together, devices. And I can see it because when I put them in upstream and downstream, I can see that the XT4 and the XT2, this one in particular, I can get 70 kA. Now, I have this statement in here, which is very important. Coordination or selectivity is to the max value of the downstream device. That's an important thing to remember, because just because it says 70, it might say T for total. Because it says 70, if the downstream device is 36, then the max you can get is 36. And it makes a bit more sense as we go along. If the upstream device is 150 and the downstream device is 120, then the max we can get is 70. We can always only get 70 or 85, depending on which breaker. But this particular breaker will be 70. If that said T, then whatever the downstream device is what we can achieve. But it doesn't. So it says 70. So if the downstream device is below 70, that's the max we can get. I hope that makes a bit of sense. The reason I put that in is because that caught me out once. As I say, that's how you learn. You add in the questions you can't really answer. But the standard, the 60947-2 standard, by definition, it holds partial selectivity and total. That's for the definitions 2.17.2 and 3. It's also in part 1 because part 1's a general rules, and I think it's under clause 3 something. I'm not going to quote. I'm not going to pretend. But that's not the standard. When we look at definitions, or when we look at, say, and if I'm flying along, try bear with me, hold the questions till the end. But yeah, there's a bit to get through, but I'll do my best to take a big deep breath now and again. So when we look at partial selectivity, without reading from what it says, that's the description in the standard. Basically, we've an upstream device A and B, downstream device B, and we can say that partial B will trip first, always trip first, to certain values up until we get to a certain point, where at this point here is where it's going to be only partial. So I have another picture on that in a few minutes. But when we talk about total, it does, exactly what it says on the tin. We look at a much better, a much nicer curve, whereas B will always trip before A upstream. But this is good for total. And as we said, and we just explained, if we have a fault here at this B downstream device, and it happens to be a higher current at this level, which trips A, well, then you picked the wrong breaker, because we can't, that's the max fault level that breaker can hold. And as you can see, our upstream device, as we said, our coordination is up to the max ICU value of the downstream device. So it's there. Anything after that, it's a problem anyway, because the breaker shouldn't be there. Let's see, can we make it a bit more clear? So when we're looking at current, we go back to current, and I have an example. When we're talking about current selectivity, it's simple devices like the XT1's, a thermomagnetic, adjustable TMA, TMD, with still thermomagnetic breakers, or we can have any sort of, let's say, MCB downstream, where an MCB has a fixed curve and thermomagnetics have a bit of an adjustable curve. But we're looking for the downstream. Now I'm only picking small values, 1 kA. If we're using current, we pick a device. Whether this one is an MCCB, we pick a device that's suitable for whatever that may be, 20 amps, 25 amps, and it's suitable to cover 1 kA. That could be 10, and this could be 30. The principle is the same. And then we look at the upstream is 3. So we'll say, okay, let's pick another device. And we'll make sure that the minimum value of the upstream device is above the maximum value of the downstream device. That way you've got selectivity. This might be very much be, as you can see, a partial solution. It's a partial solution, but it's giving you total selectivity based on your conditions. So you only wanted 1 kA. So we got it, we achieved it. That could be you only needed 10 or you only needed 22. And therefore a partial solution can give you total selectivity depending on your design or your criteria, I suppose. I'm not going to talk too much about pros and cons. The only thing I'll tell you about what we'll say about current is, because we're picking breakers with big bandwidths, bimetal strips, things like that, and they have hot and cold, we generally pick a breaker at a much bigger size for upstream. So we have a downstream, and then if we're staying with thermomagnetic, we go upstream. It's usually bigger, so the gaps get wider, and we can grow quite big. But generally, when we're looking for selectivity, good selectivity, we jump into time selectivity. It's the one we're all mostly familiar with. I would think, I don't know, maybe I'm wrong, but I'm mostly familiar. But everybody that's doing a study will generally, thermomagnetic might be near the bottom, the bottom of the pile, and then as you move up, you're going to be going with time selectivity. And time selectivity is where we will introduce electronic breakers, LS and I, L being long term, so it's pretty much the overload of the breaker. I being the instantaneous, the breaker will trip as fast as it can, and then we introduce S, and S is the selective, or the timed short circuit, as sometimes it's called, where we introduce T2, and T2 is what we do is when we set the curve of the S protection, we're allowing the downstream device to trip faster. So we're just giving it time. And normally, and this is, I can hear the questions, the little notes and all are going down. So normally to get selectivity, we switch off or disable the I function and we use the S function. And in logical terms, if you think about it, we can't tell something to trip as fast as it can trip instantaneously, but hang on a minute. You know, that's not how life works. It's like, you know, go out that door, but you close it on me. Do you know what I mean? It's not. So that's why now that creates another problem, and as we'll talk about in a few minutes. But I can feel people telling me that I'm wrong there. But anyway, let's that's where we start off. We start off with disable the I and bring in the S. That gives us a bit of time. Okay. But what we've done here is we've introduced a gap. I think. Go back there for a sec. One, we've introduced electronic breakers. We have standard, you know, electronics with dips, and it doesn't matter what manufacturer you use, the logic is the same. We use L, S, and I as other people use. I don't even know what they're called, IR or IO, I think. But it's different, but it's the same logic. We have the same three settings that generally is used. But we also have advanced features. Now, advanced features for simple selectivity, there have no real advantage to us for simple selectivity. But the problem is this for time saving. This is where, in today's world, this is becoming a big problem. So we've introduced a time here, and I get asked what is that time, and I don't know. It's how long as a piece of string type of answer. So what generally we'll do is, with ABB software, you can just drag the curves away from each other, and it will come up on the bottom, full selectivity, pull the curve back down, it could say partial selectivity, and so on. Or another, you can change the curve setting, the times, and it'll say, okay, you achieved it. And you think, oh, that's great, but it's a bit long. It's 100 milliseconds. I want it to be 70 milliseconds. And you drag it back down. The curves might look like they're parallel, but it might also depend on the opening time of the downstream device, the physical opening time. Some breakers can take 40 milliseconds. You know, a little breaker might take a bit longer. But what we've done is, now if we transfer the fault to the upper line, okay, so now the fault is here. And if we take it that it's not the only breaker in there's not only two breakers on a lot of the installations now. So just say working on 100 milliseconds. What we've done is we've added in a bit of time to allow the downstream device to trip. 100, 200, 300, 400. Now I'm just using 100. It could be 75, it could be 50, but I'm using 100. That means this being the new A, this being the new upstream, the top breaker, your main switch room, the main breaker. When we have a fault at that area, we've just told it to slow down by 400 milli. Now it's not 400 milliseconds; it's 400 millisecond curve. So, but it's still a long time. We've added a long time in energy. 400 milliseconds is forever. Yeah, for you and I, it's less than half a second, so it's the blink of an eye to us. But in energy wise, it's a massive amount. Now, that's where the problem rises. We need to fix that problem, because now we've introduced the arc flash mode. So we've gone into. Woo, I don't think I'm not sure anybody heard that, but that was an explosion that happened there. But you can see, my point is that when we go back to the stress we mentioned earlier, the stress that a breaker takes to withstand or to hold on to a fault for 400 milliseconds, that stress is added to switchgear, added to buzz bars, added to cables, doors, and all that type of stuff, hinges. It's all stress is all there until that breaker opens. So then even when the breaker opens, it's like a puff of gas, that ionized gas, that. And if I was to give you my visualization of it, let's see if I got time for this story. So I'm in inner city Dublin, inner city kid. When I grew up, and myself and my two brothers, they used to bring us. We used to go to the swimming pool in Crumlin, and it was 9 feet deep. Now, none of the three of us could swim, but the fun bit of it, that don't try this at home, is, but this is what we used to do because we were kids. I was 10, he was 15, and then 19. So we used to jump into the 9 foot deep pool. We couldn't swim. We'd blow out all our air so that we could sit on the bottom. That was the game, to see could we sit on the bottom. And then the bigger brother would hold us there until we couldn't really breathe anymore. And then we try gas and get up to the top. So if you could imagine that hold of oxygen that I was trying to do as a 10-year-old, trying to get up to 9 feet, and then at the top, just letting it all loose. It's the same with the breaker, right? That's every time I do this, that's the thought. I don't know whether it's a scary thought or a good thought, but it does bring us in. Now, there used to be sound, that it should be sound in this, but there's no sound on it. So I'm just going to play a little video. It's only like less about 2 seconds. There is sound. It's just it's a buzzing, a little beep, and then there you go. So that was a big explosion. Okay, unfortunately I couldn't get the sound to work, so it's not that important. But what that was a 100 kA fault being held by a breaker for 12 milliseconds. Now, can you imagine the stress that breaker was on if that didn't open in 12 and stayed on for 25 or 40 or whatever? And that's where the calorific value of the arc flash on the main boards is unacceptable in a lot of places. In a lot of places, we look at the arc flash, and there's one, don't be in the room. That's the one. But the other thing is, you have to trip the breaker faster. So if you have a breaker that's tripping too slow and your calorific value is 60 cals, it's not acceptable. Now, I'm not an expert on arc flash, so I'll probably getting those numbers all wrong. Your site says that's not acceptable. Bring it down to 28. The only way to do that is to trip the breaker faster. If you trip the breaker faster, you just ruined all of your selectivity study that you were just because you were working from the bottom up. And so from there, we look at energy. So when we look at energy, because I'm going to go on to zone selectivity in a sec. So when we're looking at energy, this is the part of the curve here that nobody really understands. And why shouldn't we understand? Because none of us can understand it. There's no, you can't see it by looking at it. If we have two breakers like we have here, A and B, we can see on time current, we can see that B is going to trip before A up until around about here somewhere. And then we don't know. We don't know, because after that value, and it's usually after the settings, the S settings or even the I settings, 10 times. So if we're thinking about 160 amp breaker, 10 times that is still only 1600. So, but we could be looking at energy levels of 50 kA or 25 kA. So when we're looking at this, we have to look at the energy levels in this. So every breaker, every MCCB, has what's known as what we call, a lot of people call it current limiting characteristic, but to be fair, it's more based on the let through current of the breaker. So the whole idea is that when we see a fault, we interrupt it before it gets to its peak. So MCCBs are designed to do this. Not all MCCBs, they're category A type breakers, but not all MCCBs are current limiting devices. A current limiting device like a fuse is something that will open or trip in 10 milliseconds, or half a cycle, I think it is. So, and that prevents. But the thing about current limiting devices, they're not so used so much anymore. I'm not aware of them, and ABB kind of slowed down the manufacturing of them because they're kind of special. And the reason was because they open. That's their job. Their job is to open in under 10 milliseconds and interrupt that peak. So they're great for backup. They're not so great if you're trying to throw them into a selectivity study. So that's just something to be aware. Whereas the let through current of a breaker we'll talk about when we get to the backup section. When we look at energy, and you have to be based on coordination tables or the software because it's all embedded. But for an example, when we look at two curves here, we can see A and B, and just, we can see the time current roughly 6 kA. We know and we understand, well, they'll do 6 kA. Even if that was upstream was an ABB and downstream was another manufacturer, we can still see that they're the characteristics, they're the curves. We can see that 6 kA, they're grand, but we have no idea what's in here. That's why I won't get two manufacturers to do selectivity unless an end customer decides to test them. But what we can tell by looking at the coordination tables is that that value is 20 kA for those particular breakers. So we can't see that. That's where the tables come in. That's where the online tables come in. I'm skipping over them. But now we have a problem. We've created a problem with our time selectivity because our calorific value is too high. And then we have to look at how can we reduce that arc flash, because now it's unacceptable. Now it might be acceptable in some cases, but in a lot of cases it's not. And I'm finding more and more the bigger data centers are getting, the bigger those places are getting, they're finding zone selectivity is becoming quite normal. It used to be special, now it's normal, and a Goose is special. But there's several ways as preventive, active, and passive. But we're just going to look at an active way of zone selectivity interlocking for selectivity. We do take the normal dip electronic breaker. Just checking the time, grand. And we do jump up to a slightly advanced. Now, in the older days, not that long ago, less than 10 years ago, if we were using an MCCB for zone selectivity, it was special. It was a more robust breaker. Maybe physically looked the same size, but definitely was heavier, and because of the fault levels that it could trip. And also, it had a special trip unit for ABB. It was a special PR 221 EF type trip unit. It was a bit of a nuisance, to be honest, because you had to remember to get it. And if you didn't order at the beginning, you couldn't just, download it or anything. You had to swap it out, and it was a bit. Zone selectivity, an afterthought, was very difficult in the past, and not that far past. Now we jump up to an advanced breaker, which is a simple thing to do. Be honest, the dip breakers are starting to fall off the shelves. People are starting to use advanced because we want to get ready for the future. But when we go to the zone selectivity or advanced solutions, the MCCBs and the ACBs, the trip units are the same. So zone selectivity is pretty standard now on all devices. It's a pretty, there's nothing fancy about it. It's a standard enough. But what we've done is we've taken now zone selectivity, is not just for ABB. Everybody uses zone selectivity. ABB's version of it is pretty good today. I'm not sure of the others just yet. Better look into that. Because everything was special, and it's not so special with ABB anymore. Now, what we've done is we've taken the gap, the time, the T2, and we've got rid of it. Okay, and that's a big plus for everybody in the hierarchies now, because arc flash is becoming maybe okay. And sometimes zone selectivity, normal selectivity is done to a point, and then zone selectivity takes over from there because we're happy enough with the levels of fault on the downstream. But when we got, say, 3 or 4 close to the top, let's go zone selectivity so we don't raise the bar too much. So what we've done is, anybody, I don't know whether you've noticed that, there's time selectivity, the gap, there's zone selectivity. So what we've done is, and forget about the cables because I've just mentioned that they're the same now, ACBs and MCCBs. So what we've done is we've taken a fault, a zone, any fault, the same as any selectivity. We have a fault downstream. Now, again, everything sees it. But what's different now is, I'm going to refer to blocking because a lot of people are here and a lot of people probably understand the phrase blocking. They're not blocking signals anymore. They used to be, but not blocking signals anymore. But also, I still hoover the bedroom. I don't, or the carpet. I don't vacuum it, because hoover is a known phrase. So I'll stick with blocking. So we send a signal to the upstream. So downstream device sees the fault, sends a signal. This will trip on its zone selectivity time, which can be, say, 40 milliseconds or 20 milliseconds, whatever the fastest it is, nearly instantaneous, but not, because zone selectivity is set on the S protection, or the zone selectivity is an S protection. So say 40 milliseconds, which is great. The upstream gets a signal to say, work on your standard normal S protection, which might be 200 milliseconds. So it's loads of time. And then that in turn sends a signal to the one above and says, work on your normal S. So selectivity is still working as normal with loads and loads of time. You can give yourself 200 milliseconds each place. But then we see a fault on the next line. Now the next line hasn't seen a signal from the downstream device, hasn't seen it, so it's going to trip in its zone selectivity time, which is 40 milliseconds. So now instead of being on a 200 millisecond curve, it's on a, so it's tripping pretty fast. And then that sends a signal to the up. And then the same. So this is the scenario that we were in with our 400 milliseconds arc flash problem. Unacceptable. We didn't like it. It's dangerous. These are the videos where you see people plugging in machines and breakers and then they blow up and big flashes everywhere. So we don't accept it. So at this stage here now, we have a fault. It's a high fault. But now we've no signals from downstream because downstream don't know there's any problem because they haven't seen it. But now this breaker, instead of being 400 milliseconds, is now going to trip in 40 milliseconds. So point number one on arc flash, if there's an arc flash problem, don't be in the room. That's it. Be far away from it. That's why you have the labels on. Says stay 2 meters away with this close, or don't be in the room. Or point number two is trip the breaker faster. Get rid of it, the problem, as fast as you can. Reduces your arc flash. Now I won't go through the things there, but we will say that zone selectivity reduces so much stress. Everything trips when it's supposed to. Go back to the panel that we talked. That was 70 milliseconds. Zone selectivity could take that out in that breaker out in 40 milliseconds. So that's an awful lot less stress on the switchgear. But it is a little bit. It can be a little bit complex. It's not too much, but it's getting easier and easier. When we go to Goose, how am I doing? I'm doing all right. I have a couple of minutes, haven't I? Yeah. When we look at Goose, I'll read this. It's a generic object orientated substation event. That's a bit of a mouthful, and I've done this presentation a few times, and I've talked about Goose a few times, and I have to read it. But Goose, just to be aware, is an ABB mechanism for fast transmission for talking across a IEC 61850 protocol. And 61850 protocol, anybody that's medium voltage on the line, now I'm a low voltage guy, anybody's medium voltage 61850 or Goose for ABB talking is not new. Anyways, low voltage 61850 is. Now the thing about 61850 is it's peer-to-peer, so it's a horizontal communication protocol, and it's also horizontal and vertical. So it has no master and slave. So everybody talks to each other, which is fantastic. And the other thing about it is it can be in real time. And because something is in real time, it can be used for selectivity because it's that fast. And anybody, as I said, I have pictures of IED relays for medium voltage, but now we actually are embedded onto the Emax2 for ABB. Be careful when you're looking at 61850 on low voltage breakers because a lot of low voltage breakers don't have embedded 61850 protocol modules like the Emax2, like the ABB breakers do. They have an interface, so they have a connection to a Modbus that connects to 61850. You get fast information, but it's not real time to the breaker, so it can't be used for selectivity. So just be aware of that. But it takes away all of the cables that you can see, hundreds and maybe thousands of cables if ever, and it replaced them with RJ45. The real time allows it to talk to each other. The difference between Goose, very much so, than zone selectivity, it's actually talking. It's how are you today? My breaker is fine. I'm not overheating. Current is pretty level. All my coils seem to be all my Rogowski coils seem to be all working, and everybody's happy. There's no problems, and it just constantly talks to breakers are linked up to each other. That's great for nodes, whereas you've different little islands and things that are great for communicating that way. But then if there's a problem, you can see here, it'll keep pulsing fast. So it was pulsing at just over a second. Now it's pulsing a bit faster because the information is going up. And that information might be something like this. We got I'll skip that. We got a fault on the low voltage breaker. We got a fault down here. We told it to trip. It didn't trip. Got a signal, but the breaker didn't open. Now we have a problem. Maybe it's bad maintenance or something like that. The breaker didn't open. So now straight away in real time, the Goose signal will be sent to the breaker above and said, I'm in trouble. You're going to have to trip. So stop holding out, that blocking, it's gone. Now you get in here and save the day. And at least the difference between, it's not just a signal, it's not an open close signal, it's an actual conversation. Okay, it's real information. But other than that, it's the same principle as zone selectivity. You could reduce the breaker upstream of trip as fast as it possibly can if that's the one that sees the fault first. So there's one thing I will say about Goose. If you're in that level of selectivity, then you have that competency. But the testing philosophy can be a little bit tricky for low voltage people. Now I'm just finished. I think I've got and I think I'm doing well. So the because I can hear all the little pens going down and asking the questions and stuff. But I'll just take a drink of water. So have a big deep breath. Because this is something that comes up quite a lot with me. Backup protection. Where we use backup protection or and there's a few things floating around as regard cascading is probably a better word. It's used by a different manufacturer, but cascading and backup are the same. Like discrimination, selectivity, one is used by one manufacturer, one is used by another. And the same with, say, enhanced cascading is selective backup. They're just different terms. But I put cascading because it's more readily used. A lot of questions I get is based on cascading. So when we look at backup, cascading, whatever, when we look at protection, what we're really doing is we're blanking off selectivity. We're saying it's not that important to us at that particular area. And because what happens when we look at the concept of backup, it's where we're using if we're using a current limiting device, it's going to open really fast. So it's opening, and the let through current to the downstream device is less. So we're protecting we might be in a, say, next slide, 100 kA area. We want to use a lower, cheaper, shouldn't say that, but a lower Ka downstream, because what's happening down there is not too important. But we were concerned that, say, a 36 Ka breaker is in the wrong place because it's in a 100 Ka zone. So we decided to use a backup. But what it means is that this is the best slide. When we look at discrimination or selectivity, the same area, we have 100 Ka. Okay, that's the zone here. We pick a breaker upstairs, a T5L. That's me timer to tell me I have about a minute left. The upstream device, T5L 400, already 100K. It's already in a big expensive breaker. We've already put in our few bob in there. But now we have the downstream devices are also 120K because they have to cover the 100K because we want selectivity, we want backup, or we want selectivity, we want discrimination. Okay, so that's the design. But then when we look at the backup version of it, we still have the same fault zone, but we pick a smaller breaker, 120K, but still an XT4 250, quite a considerable amount of physical size and price wise. But then downstream, we're picking 36 Ka breakers. And the reason for that is that the upstream device is going to back them up. But what does it mean? What does backup really mean? It means that if we have a fault in this area, the upstream device will trip. Maybe both of them. Maybe you'd be lucky in the downstream device, but really that's why it's in here. Because at 100 Ka here, this breaker will open. The let through current when that breaker opens, and they normally be with MCCB's category A breakers. The let through means that the downstream will not see 36 Ka, so it won't be damaged in any way. A lot of times backup is used when there's a machine down here that's worth a couple of million quid or whatever, and you don't really care if the lights go off in the building as long as the machine is protected because it's worth a lot of money. And the machine might only be rated for 36 or 26 Ka, but it happens to be in a place where there's a possible rise of 50 or 100 Ka. So you put in something to reduce that let through energy. And the same happens. So backup generally means that there's no power there's no reliability in the power. You're not really concerned. Okay, so that's the good thing about it is it takes away an awful lot of stress, but breakers trip. And that's the last slide there is just a note for the next CPD. Hopefully someday we'll do on 61439 standard. That's it. My email address is on the bottom. I'm open for questions. So any questions is there, walk away. If I can't answer them, I'll take a note and we'll do our best to get back to you. But there's my email. You can directly contact me if you have any low voltage solution problems, and we'll do our best to, myself and my team, we'll get back to you.